Causal relationships are important, but they have been overlooked in many statistical analyses, which lead to many problems. Today, I will show you an example related to thermal comfort. My name is Reggie. I'm a PhD candidate at UC Berkeley, and I would like to thank many of my collaborators in this work, and also the financial support from Center for the Built Environment. Let's start with correlation. A correlational relationship is non-directional. A correlates with B is the same as B correlates with A. For example, on the left side, the graph shows a correlation between air pollution in Boston and ice cream consumption. However, it doesn't matter which variable we put on the x-axis or the y-axis. The correlation coefficient, or the R value, will remain the same. To evaluate the correlation coefficient, we can also use other statistical methods. And one common method is linear regression. Let's look at the left side first. For a linear regression, we first need to assume a linear relationship between two variables, y equals ax plus b, for example. Second, we need to add an error term that represents the difference between predicted values and actual values. Third, we need to minimize the sum of all errors, and we can derive the model coefficients A and B. We call the model coefficient A as the correlation coefficient, and it can be visualized as the slope of the regression line. Then, at the right side of this slide, I switched the position of x and y-axis. Initially, I thought this switch doesn't matter, and the resulting linear models would be interchangeable with the left side and right side. In other words, the model coefficient AI equals to 1 over A2, and the model coefficient B1 equals B minus B2 over A2. However, I later realized that this equivalence only holds when the error term represents the orthogonal distance between each data point and the fitted line. And this regression method is called total least squares, or TLS. When the error term represents the vertical distance between each data point and the fitted line, the regression method is called ordinary least squares, or OLS. And indeed, the OLS method is the most common one we use, and is also the default regression method in Python and R and other many programming languages. Therefore, for OLS regression, the direction of the regression matters, because when we put different variables on the y-axis, we are minimizing different error terms, and the resulting linear models would be different. A statistical mantra says that correlation is not causation. A correlational relationship describes an observed pattern between variables, or one variable increases, another one also increases. In contrast, a causal relationship means an actionable mechanism where if we made changes on one variable, it will lead to another changes in another one. So we might want to use the correlation for prediction, but we have to rely on causation for decision makings. And the problem is really we tend to misinterpret correlation as causation. Before I go deep into a thermal comfort example, I want to emphasize the importance of this causal diagram tool. It provides a language that enables us to visualize the causal relationships or causal directions that we usually assume in our statistical analysis. Without this language, these assumptions become ambiguous, and we would be more likely to misinterpret the correlation. In many thermal comfort studies, people would like to collect two kinds of data. One is the indoor temperature measurement, and another one is the occupant thermal sensation volts, TSV. -3 means cold, 0 means neutral, and the +3 means hot. Then people also would like to conduct a linear regression using the default OLS method. And commonly, they put the TSV on the y-axis and the temperature on the x-axis, because they think the temperature is the independent variable, and the thermal sensation volt is the dependent variable. From a causal perspective, the causal relationship is from temperature to thermal sensation volt. And the reason that people do this linear regression because people want to calculate the neutral temperature and the comfort zone. And they can be calculated based on setting the TSV as 0 or plus minus 0.85 on the linear regression line, and people can find the corresponding temperatures. We call this regression approach A. And interestingly, some researchers run this regression in another way around by putting the indoor temperature on the y-axis and the thermal sensation volt on the x-axis. Some people did this by mistake because in the code, it's actually easy to confuse the position of x and the position of y, as shown at the bottom, like in the Python, the x-axis should come first, but in the R, the y-axis should come first. But most of the time, people did this reverse regression because they think that the regression direction doesn't matter, or either approach would give us the same estimation result of neutral temperature and comfort zone. But we used the same building data set, and we found that this approach B would result in a very different neutral temperature and a much narrower comfort zone than the approach A. And the difference of the comfort zone is about 10 degrees C. This huge difference of comfort zone will lead to significant implications on occupants' comfort and also building energy consumption, because we commonly apply these comfort zone values as the HVAC system's temperature set points. And we consider the difference between two regression approach from a causal perspective. And we think both approach have different causal assumptions. In approach A, it assumes a causal relationship from temperature to thermal sensation. And we think this approach A is mostly applicable in climate chamber studies, where researchers manipulate the temperature and observe consequent variations in occupant thermal sensation. In approach B, it assumes the opposite causal relationship, which is from the thermal sensation towards the temperature. It means that different thermal sensations can trigger adaptive behaviors, such as when you feel hot, you would like to open windows or using fans, which in turn that will alter your surrounding indoor temperatures. We think this approach B could be more applicable in certain few studies in actual buildings, where occupants could have significant controls over their thermal conditions. The approach A is the most common one people use for developing the adaptive comfort models, including the ASHRAE standard 55. However, the approach B is more aligned with adaptive comfort theory. And currently, we are using this approach B on a larger ASHRAE, the Global Thermal Comfort Database 2, and we find that the resulting adaptive comfort model is quite different from the one in the ASHRAE 55. The main takeaway of this presentation is that we want to stress the importance of causal thinking, which specifically is scrutinizing the causal assumptions underlying statistical analysis, including other machine learning algorithms or data-driven models. Neglecting to do so will lead to correlation-based decision-makings, and consequently, the results will compromise occupant comfort, building energy consumption, and also the sustainability of the built environment. If you're interested in this topic, feel free to email me, or you can read our recently published paper. This presentation is mainly based on the first one, and it should be open access to everyone. The second paper is another example related to building energy simulation, where we compare the results of different machine learning algorithms, and also we found that causal thinking is extremely important.